Okay, we're recording. Okay. Okay. So here are the review topics, right? And yeah, we need to be, really familiar with delta steps, ramps, exponential decay, integration, sampling, a little bit of complex numbers, plotting composite functions, voltage division, non-inverting op amp, and actually inverting op amp too. And of course, convolution. All right. Now, usually, it's the Laplace transform, but we speak so quickly and we use such a shorthand that sometimes we just say Laplace, and that can even be a shorthand for taking the Laplace transform, doing something, and taking the inverse Laplace transform, all by just invoking this one word. All right. And what we do is we find a function in the complex plane, all right, where theta and omega are real numbers. And when you multiply a real times an imaginary, you get an imaginary. And so we have, ultimately, we have a real axis and an imaginary axis, right? This f of s is here, but it takes as one of the inputs a time domain. So if we take something in time, right, it converts it to something in frequency on the complex plane. How does it do that? And there's some interesting things that when you're learning can probably bite you, if you will. But notice how it starts at 0. Now, sure, we can time shift things whatever we want, but by having a lower limit here, that means built in to everything is a step function. So this might be the transform itself, but we're going to find that when we go back and forth between Laplace and inverse Laplace, you have to add that step function back in, right? The other thing is this isn't like the dreaded time domain convolution where we have tau as an integration variable where it's not equal to RC, okay? Which I know causes a bit of confusion, right? And probably the best way to understand it is just to do one. So let's find delta S. All right. Now here's a convention. Notice time domain, lowercase function of t, f, or the S plane, right? Upper case of S. So I want to find the delta function, and I want to find the Fourier transform of the delta function. So that would be capital delta which just equals 1. Okay. Now, you might feel that that's not, I should have more steps doing integrations, but really, this is practically by inspection, or effectively. And if you think about, if you remember the sampling function, right? If I integrate over a range where delta is active, I'm going to get that value, right? So delta t minus e to the t, right? That becomes 1, right? And since that would be, and then here, it goes to infinity and it drives this function to 0. Now there's a little more to it than that, but if you look it up, it's pretty much just said by inspection. All right. So it's not a great example of learning the Laplace transform. It's better to do the actual step function. So U of S, okay, and I'm going to put U of t, e to the minus st dt. Now notice, we're starting at 0, right? And what that means is we're integrating from time equals 0 all the way up to infinity. So ut is 1, right? And so and now you can begin to see that there's always a step function. All right. All right. What's the what do I need to have to make the derivative of the integral equal to the derivative? I need to have 1 over s. I need to have a minus. And of course, exponentials are always like that.
Professor, I have a quick question.
Sure.
What's the e to the power of? Is that s or delta?
This?
Yeah, is that s? Is that s?
S. Yep.
Yeah, it's
S.
s. Okay, it looks like delta to me. Okay.
Oh, yeah, I can see that. Sorry about that. Just so you know, I bought a desk. It's in the mail, and the handwriting should definitely improve. So e to the minus infinity goes to 0. E to the minus 0 goes to 1. Minus, minus. I get 1 over s. Okay. And really, I've done them. I've done a step. I've done a ramp, which the ramp is actually in a way, the hardest one, because you have to go back and remember integration by parts. Or maybe you realize you can get away with SIMPy and do integration. And there's an exponentially decaying function. Okay. Now, there's just another. So if I want to denote taking the Laplace transform, I just put an L. All right. And this is the time shifting property. And it is almost, like by inspection, right? Because, if we do this, we know it's just a step function delayed by 1. And so when you go through the math, this is the only thing that when you take the Laplace transform of something, that will make it work. All right, so the Laplace of ut minus 1, well, ut is 1 over s, certainly, but then the delay is just shown at the shown like that. And then what happens is when you combine, this is where the kind of the addition of the time delays comes up. And we can do an example of that. But this is another relationship. They just prove that it works. They don't actually derive it. And sometimes I think when things were originally developed, they kept guessing until something worked. And their guesses might have been logically based guesses, but they just found something that worked. And of course, for time shifting in the frequency domain or the S-plane, this is the one that works. Okay. Now, so I just did them, and you can go through, but really, if you were in differential equations, you might be asked, derive the step function, the Laplace transform of the step function, derive it of the ramp function, derive it of exponentially decaying, derive the time delay, or prove the time delay. But in this class, I'm just doing that to kind of remind you where it comes from and trying to tell you that because that lower limit is 0, there is a step function built in, right? Also, in lab where I'm introducing you to symbolic math, that essentially you can create your own Laplace transform table, all right? And since many Laplace transform tables exist, it's easy to check your work, all right? But there won't be a question on the exam, derive any of these, because what everybody really does is you just have a table, okay? And in this table, now the delta function, does that have a step function in it? Kind of, but the delta function, I guess, is like a step. It doesn't need further definition. But the step function, of course, is the step. The ramp is t times step. Exponential decay, yeah, you need to add it in there. And even a sine wave, to actually do the Laplace transform, you have to multiply it by a step. Same with cosine, all right? But you just use a table. And that brings us to the inverse Laplace transform, which there is an equation for it. But when I use this in my work, I tend to try to find the closest thing and then modify it to go backwards. So I've used the Laplace transform to go from left to right, but to go from right to left, I just look at it. Oh, I have a constant. That's going to be a delta function. I see 1 over s. That's going to be a step, right? And so on. Now there's more than this, right? There's more transform pairs. And the thing is in some ways, this is almost all you need for first order type circuits if you use partial fraction expansion, right? But that is a little bit difficult to deal with on an exam. So in my recommended cheat sheet, which you can find in the Canvas shell, I have the most common ones. And then there is something, and this is a heads up, okay? Is that if I come up with a function of s that looks like this, right? You can't just go straight to a lookup table. You have to know, are A and B real and opposite? They're real and different? Are they real and equal to each other? Or are they complex? And depending on that relationship, will tell you which thing to use. Now, if this sounds familiar, A and B, two numbers that are real and different, two numbers that are the same and real or repeated, and two numbers that are complex, if that sounds like overdamped, critically damped, and underdamped, you are right. That's exactly what it is. All right. But rather than, and then maybe like a word of advice is that the book can tell you a lot of tips and tricks first, and then show some examples that by the time you get to the example, you forget what the tips and tricks are. And they do start with in convolution with a very difficult example. All right. They have a triangle and they convolve it with an exponential decay. Okay. Now, this could be 10 pages to do, right? And even with the Laplace transform, it can be hard. What you have to recognize is that this function is RT. For example, right? So if I want to find this convolved with this, right? That looks quite complicated, but really, these are all I might have 3 of them, but I have all I have to do is find this convolution and then multiply by -2, delay by 1, and then multiply by 1 and delay by 2. So I can kind of easily come up with the equation. But here's the thing. You have to learn to anticipate what the plots are, because actually coming up with the equation's not so bad. But because this starts and ends at 0 and this starts and ends at 0, the function
Professor,
time is,
for the last
yeah, shoot.
ramp function that you wrote, shouldn't it be t minus 2, not plus 2?
Oh, yeah.
Okay.
Yep. Thanks. So anyway, I can do some things right now. Is that this is 2 seconds long, and this is effectively 5 seconds wide. I know that the resulting output is going to be 7 seconds long, and that everything is effectively going to be some kind of t time convolved with exponential. And so I'm going to get some kind of curvy thing that does this, right? So what is it point by point? What is the max? What's the exact shape? Well, that's actually maybe a little more involved. But the fact that it's 7 seconds long and that, you know, we have a linear times exponential decay, there's going to be exponential decay in the answer, right? That we're just going to get something like that. Okay. But that's just kind of a hint as to where we're going. All right. So now we're going to use the Laplace transform to do convolution. And in the notes, I did a more complicated example. So what I'm saying is that's all like an overview. All right. So let's say, what if GT equals UT? Okay. What if HT equals UT? All right. It's always good to plot things just to get an idea. All right. So that's a step. I step up, but at the same time, I start going down with a slope of 1. And then the two slopes cancel each other out at time equals 1. So I have a triangle. So what I like to do is just kind of give a quick look of what things look like. Now, yep, I'm going to do the convolution integral, except I'm going to swap it around a little bit. Okay. Reason is now I can draw this the same, right? But I'm flipping the step function. So this is t and it's tau, right? So what happens is I increase t as I go along, but the minus tau has reversed the shape. So I'm dragging it across. And then eventually I start taking slices, right? Now notice when it starts to overlap, I have a constant times a linear, right? So a linear t should, there should be t raised to the power 2 in there somewhere, right? And you can see that the area is increasing, but the overlap is actually decreasing. So I add a wedge, and then I add a wedge and add a wedge, but the wedges keep getting smaller and smaller. And then at some point, right, I can have the parameter t here, or I can have it out here, but that overlap area is still the same. Integration is, you're finding the area. So the area is going to start at 0, right? It'll increase with a wedge, but then the wedges get smaller. So I should see something that starts low and ends high and maybe goes sharp and then decreases in smaller steps. All right. So let's see how that works out. So I didn't really do the integral, right? I could. I'm doing this drag and drop thing in my head, or this is a rough sketch, to see what shape, what final shape should I get? All right. All right. So g of s was a step function, right? Because the time domain, the step function was a step, so g of s is just a step. I looked it up. The h of s, h of t was a step, so that becomes this. The then there was also a ramp, so I just look it up, right? These happened at 0 time. I mean, there was no shift, right? And then the Laplace of that ramp there, again, a ramp doesn't matter. I can scale a delay to all linear operations, but here's where I do the delay. Since I was delayed by 1, I have that. All right. And then, yeah, f of t, I mean, sorry, f of s equals g of s multiplied by h of s. And that's the thing. And it's kind of important. So I'm just going to write it out again. F of t, the convolution of these two signals is g lowercase, h lowercase, functions of t with the convolution symbol, right? But in Laplace, that convolution symbol is just replaced with multiply. So things that are calculus based, like integrals and derivatives, become algebraic things in the S plane, right? And so what we do is we convert things to the S plane, multiply them, subtract them, divide them, right? And then take the inverse Laplace transform, all to avoid the calculus. All right. So all we have to do is multiply this out. Now, to find that function, now I take the inverse Laplace. All right. And here's the thing, it's all linear combinations one way or the other. So all I have to do is find the inverse Laplace of this, the inverse of that, and the inverse of this. So if I look this up on the table, all right, what you're going to find is that you get t. Okay. Here, I'm going to get minus t divided by 2. And as you know, there's that this is non-zero. Ft will be non-zero for time less than 0 if I don't do something. So I have to put the ut back. And then here, you just have to know that this is a delay of 1. So wherever you see a t, right, here's a t. It's going to become t minus 1. So if this is t squared, it's t minus 1 squared. Wherever the ut is, the ut is going to be delayed. All right. And so this would be the final equation, which might look a bit confusing to plot, right? Because you're like, well, it's t, but then it's minus t squared. And so if you don't know what the shape should look like up here, it'll be quite confusing. And sometimes you will have to substitute back things in. So let's just break it up, right? We have time less than 0, right? Ft is going to equal 0 because everything is times a step, right? Well, what about between 0 and 1? And I'm going to rewrite the equation. Well, between 0 and 1, this is active. Between 0 and 1, this is active, but this is still 0. So actually, in this regime, f of t equals right, which equals t all right, which if I plot it, right, before t is equal here. Now here, what I've got is something linear. And when t is less than 1, right, this term is going to dominate, right? So it'll be linear. But then this squared term is going to kind of overpower it and keep going down like this. Okay. But remember, we only said I'm just going to call this 1. Okay. So it comes up and then it goes over. But this isn't valid because we said it was only for this time frame. All right. So what about I'm just going to draw it over here. What about when t is greater than or equal to 1? All right. RT is still active. Minus RT squared over 2 is still active. And then this is becoming active now. So now everything is active. All right. So now FT is going to equal T UT minus T squared divided by 2 UT plus T minus 1 squared 2 right? But again, I've said this already, we're only in this area. So I can get rid of all those UTs. Right? Now, this one might be a little bit still hard to figure out, and you have to expand it to really see. All right. So the first part is going to be plus t squared divided by 2. Then I'm going to get minus t. Then I'm going to get plus 1/2. So this t cancels here. This t squared cancels here. And we're left with a constant of 1/2. So that's what we get, which is what we anticipated just by kind of sketching it out, right? Oh, that's... Now what this is I have a step minus a step that's delayed. So I have a rectangle, but here's the same triangle function. Here's the convolution, and notice it starts at 0, kind of linear, and then it rolls off. And then stops rolling off at 1/2, and then it's constant. And then the only thing I did was, oh, I've got another step. This time it's inverted and delayed. And in fact, then I get the reverse out. Now this takes kind of a long time to do by hand. But if one recognizes, and you get this shape, actually what I'll do. So here's the problem we just did, right? Now, remember how I talk about composite functions, right? Well, if you think about it, this is like a composite function, right? Where I have a ramp, I subtract the ramp squared divided by 2, and then I add a ramp delayed by 1 squared divided by 2. Well, look here. Now I'm subtracting a ramp delayed by 5. I'm adding a ramp delayed by 5, that's squared. And then I'm subtracting another squared ramp that's delayed by 6. And so if one could recognize, yeah, that was my shape up, that's my shape down, right? And how would you know that you should do that, right? Here's my rectangle. It doesn't matter which way it is. If I flip it, it's symmetric. So, and then I start drawing it across this shape, right? So what happens is that the area starts to increase, area is increasing, but it's not increasing as much. And then I reach this point where it's not increasing at all, but it isn't 0, it's just not increasing, right? Then as the back end starts to leave, right, the overlapped area is going down, right, back down to 0. So if you see two shapes, you know, length of T1 and the other one is a length of, I see it. I'll answer you in a second. Right, this whole time, right, it comes down at 6, right, which was 5 plus the 1.
Hey, Professor, can you hear me? Because I can't hear anything you're saying.
I can hear you.
Oh, good. Now, oh, suddenly you're back. Can you try speaking
I
again?
don't know, maybe I'm just moving my lips.
Oh, good. Oh, good.
Testing, testing.
Oh, that's a relief. Suddenly I can hear you again. I was like, what's wrong?
Sorry
Oh,
about that.
oh, none at all. Please continue.
Okay. Okay. So anyway, again, Now, the example I did in the notes was the rectangle, right? Which it really starts to get involved. All right. If you do it like that. But really, okay. So I have 1, 2, 3, 4, 5, 6 delta functions. And I have one, oops, step function, right? So I really don't want to draw it out again, right? But that means I have a step convolved with delta, step convolved with delay delta, step convolved with delay, delay, delay. And so really I have a common function of delta convolved with step, which right by definition is UT, right? But let's do it the Laplace way. All right. So f of s equals g of s times h of s. So the delta function becomes 1. So there is a e to the minus s 0, right? So it just cancels out. Times 1 over s. Okay. Now I want to find the inverse Laplace of that, right? So f of t will equal L inverse, and I'm not going to redraw it. right? And so this becomes step. I get another step, but I have the delay. I get another step with the delay, right? And I think you can see the pattern here, right? 0, 1, 2, right? 1, 2, 3, 1, 2, 3. I'm at 3, right? Minus a delayed step, minus another delayed step, minus another delayed step. Staircase up, staircase down. Okay. Now, this really is a lot of work, right? Even though we kind of already know. And so that you can do that find the common function in the Laplace as well, right? Is that we recognize that z of t equaled delta t convolved with u of t, so that z of s would equal 1 times 1 over s, right? And that the inverse of 1 over s is ut. So that's to think about it, right? That delta function converts to 1 in the complex plane. This convolution converts to multiply in the complex plane. And then when you take it the inverse back, you get exactly what you put into it. Okay? So trying to prove that a delta function kind of samples back whatever you gave it, you know, it can be done, but when you do the Laplace transform method, right, that delta function becomes 1. 1 times anything is the thing. There you go. All right. And so if you look at the homework, right, yeah, I have staircases, I have many things, right? Things that you will have seen before. All right. But maybe not that particular example, right? Now, again, just I'll point it out. I have office hours and you get extra credit, and it can be a very efficient way to get unstuck. Okay. But in class, you know, I can't really give individual attention, right? So I don't know how you're individually stuck. Yeah. Okay. Oh, yeah. Okay. So the question is, hey, what do I do if it overlaps with class time? Email me. We'll set up a time. Okay. Just so you know, I have a lot of other things to do, but talking with you all is like a nice rest for me, and it's an enjoyable activity. So now, truthfully, yeah, I might be busy, and you know, an hour before it's due is going to be tough. All right. Now, You might be thinking though, why do I have to learn the Laplace? We already did delta ft in the time domain. We did ut, and I'm not going to draw these out. We did rt, ut. We did rt convolve with rt. We did delta step and ramp convolved with exponential decay. We did scale and delay. Why? Well, actually, so if we've already got all those functions and all we have to do is scale and delay, why bother with Laplace? Well, I'll tell you. Is because many times, in fact, we will spend so much time starting in the complex plane, okay, that you might forget the transient response exists. Okay, so here's a circuit, right? I want to find h of s directly. I don't want to deal with the natural response and all of that. I'd like to be able to use, because natural response, right, that involves the derivative of something equaling the derivative of something, and then kind of guessing what function will do that, right, which is a decaying exponential, right? Or we can use algebra. I for one, want to use algebra. So if I say Vn of t equals ut, Vn s equals 1 over s. If I say Vc, no, oops. If the current through a capacitor is the capacitance times its derivative, yep. H of s is the transfer function. Thanks for pointing that out, Brandon. What'll happen is you'll get used to this so much that you won't even recognize the word anymore. You know it so well, right? So we've already talked about voltage division here at this node, right? And I'll call that V plus, which is ZC, ZR plus ZC, all right, which is 1 over SC now. It's best to multiply through the S and take out the R. And I'll tell you why. That 1 over RC, that RC, yeah, that is tau, right? The time constant of a first order circuit. But that 1 over RC is actually omega naught in frequency, which we've been using as alpha, all right, so far. But this is in a very important form because it tells me something important about the system. The first thing is that it's a definition of a pole where h of s goes to infinity. So if, or the magnitude, all right. So if S equals minus 1 over RC on the complex plane, this goes to infinity, which when you plot it, looks like this, because you can come to that point from two different locations. And so that looks like a pole. All right. And so having it in this format, right, also can be converted to where you're all in the frequency domain. All right. That's just a way of doing it. I caution you for not doing it this way, because those that come up with their own way get lost. Right is right, and I don't have a problem with that. It's just you could try it a different way, but if you get it wrong, right, it's wrong. So that first portion, right, I'm just going to redraw it, the equation. All right. And the second part was just this. Okay. And this is where you kind of have to start really knowing things by sight. When I look at this, I say, oh, you know what this is? That's a non-inverting op amp. The gain is 1 plus R2 over R1. So whatever's going in here is just multiplied by that. Well, I did this by voltage division. I recognized it. Okay. So on an exam, yeah, you can say, I found this by voltage division. You could even say by now inspection. In EE98, you were asked to come up with this equation. Oh, that's a whole other deal. All right. So now I have this, and I want to know the step. Well, G of S still equals 1 over S. All right. So F of S equals 1 over S times 1 over RC. Oops. Which is just a constant, right? Now, you can either look this up directly or use partial fraction expansion, all right? But really, you can use the table. That's what I do. So this does exist in a table, but it'll look like this. Okay. And alpha would be 1 over RC. Now that's just a scale factor, right? So if I take the inverse Laplace of this, well, that scale factor is just a scale factor. I redraw it. And then this, however you do it, okay? However, this will not be correct for time less than 0. So you have to add back the step. All right. It's probably just easier if I There's this professor at Swarthmore, and I like a lot of what he does. So here's the Laplace domain, here's the time domain. Now, yeah, you'll see it a lot like this, but you have to understand, if I'm going back and forth, you have to put the step function here. He's just, excuse me, left it off for convenience, okay? But if I look up, so here I have 1 divided by s, that's plus a. Then I get 1 over a, and then I get this familiar function. But remember, we had an alpha here already. So it works out, okay? And then it gets even faster. What if I did a high pass? Okay. H of s of just that part is ZR to keep it in his terms, I'll do it like that, right? Well, then I just feed that into non-inverting amplifier, right? So that here's my gain. Here's my transfer, complete transfer function, right? G of s equals 1 over s. F of x equals these two multiplied together. Here's my gain. Now I have 1 over s plus a. Just for looking it up, right? So really, I just did question 1 on the midterm is f of t equals something. You figure it out. Question 2, find this convolution and plot. And you can do it either any way you want. Question 3, is this or this, and you have to find the transfer function, which we started today, right? Then you have to find step response, right? Which we did, and plot. Now there's 2 things in between that we're going to start later that are the Bode plot. But that's question 3. Question 4 is a Bode plot, and 5 is something else. Hey, Tran, can you hear me now? I'm gonna
Professor, we
turn
can't
this
hear
off.
you.
Yeah, I can hear you, Professor.
Testing.
Yeah,
Yeah, we hear you.
All right, I turned off my headphones. Not quite sure when.
Just start at the beginning of question 3, please.
I'll just, yeah. What I'm saying is, these are the midterm questions, right? Question 4 is something called a Bodie plot we haven't done together. And 5 is like a thought question. But really, you have the low pass, the high pass, right? You need to derive this. Then there's 2 things that you don't know yet. Then find the step response and plot it. Okay. But you can see that there's a lot that goes. And this one, in case you didn't hear, is I'll give you 2 functions, which are like steps and ramps, decaying exponentials, and I have you convolve it and plot it. Okay. And I, just to point out, module 11 is the midterm, and I have previous solutions. Okay. If I don't publish a solution, that means I don't like the way I answered it. The answer was right, but I've changed my procedure to try to find an easier procedure for people to follow. And so I don't like people seeing the old solution because they might get distracted by it. All right. But probably now is the time to start reviewing this kind of thing, right? Here we're still learning, right? And looking at when the homework was due, I thought maybe I could. I'm trying to make sure people don't fall behind by going too fast, but I can't, I can't make the assignments due whenever. So it's kind of an optimization problem. So I changed homework number 4 to when that was due. All right. Because homework number 4 is very close to like maybe exam questions you might see. Right. B is A and B here are really kind of like warm-ups. All right. But 4 is very close to the Bodie plot type questions, almost like a question bank. Okay. That's pretty much what I have for today. The notes might have, more detail and, where I went and derived it more in detail, right? But when I look at this circuit, I say, oh, that's voltage division. And I'd write it out and then derive it. And then I'd say that is a non-inverting amplifier and the gain is such. And I multiply these 2 things but together. I don't start writing KCL and any of that. All right. Because when I'm grading exams, those that do tend to be a little bit lost and tend to run out of time. Okay. But now is the time to start actually reviewing for the midterm and checking to see whether you know it or not. All right. And if you want to come to office hours and learn more about how to do that, well, come on by. And then you can even tell everybody on Discord. All right, guys, I guess I'm going to end it there.
Have a good day.